What is up, young chemists? Mr. Rosen here. Today we're talking about solubility curves. We're going to just sort of talk about what they are, the different parts of them, and then reading and interpreting a graph with many solubility curves plotted on it. So this is in our solutions unit. A little bit of background and vocabulary, I guess, first. So there are some terms here in bold, some words that are frequently used with solubility curves. So, as it says, the solubility of a solute in solution is a measure of how much of the solute can be dissolved into the solvent, and it depends on how much solvent and what the temperature of it is. And also what the solvent is. Sometimes the solute doesn't really dissolve to any appreciable degree, and that's what we would call insoluble, meaning it doesn't dissolve in the water. It doesn't go into solution. All right, so an insoluble solid remaining is referred to as a precipitate. Solvation is what it's called when the solute dissolves into the solvent, when it gets pulled apart by the water molecules. And there's a limit to how much solute can be dissolved in a given amount of solvent at a given temperature. So when a solution contains as much solute as will dissolve at that temperature, we say it's a saturated solution. Okay, meaning once you reach saturation, if you added more solute to it, it wouldn't dissolve. Okay, so to get a little bit more concrete of an example, if you had a beaker with, let's say, 100 milliliters of water in it, and you added some salt and stirred it around and the salt dissolved, that's an unsaturated solution. Okay, if you added more salt to it and it dissolved, that's still unsaturated. If you add more salt and it dissolves, that's unsaturated. You continue to add salt until at some point you add the salt and you stir it around and it won't dissolve any more salt. The crystals will just settle to the bottom. Okay? If that's the case, you have made a saturated solution, meaning that amount of solution at that temperature has dissolved as much solute as it can. That is what is plotted on a solubility curve graph. So I'm just going to have one solubility curve here. Let's just say one thing, potassium nitrate, KNO3. Okay, this could be an example of a solubility curve for just one substance. Okay, now this line represents the saturation point, meaning if you are on this line, that's the maximum amount of KNO3 that you can dissolve in 100 grams of water at that temperature. So this is a little confusing to some people. On this axis, if you look, it says solubility, grams per 100 milliliters of water. So you could think about this as having a beaker with 100 milliliters of water in it. Okay? The beaker with 100 milliliters of water in it, you can dissolve a different amount of KNO3 in that beaker of water at different temperatures. So this is how many grams of KNO3 you can dissolve in 100 grams of water at these different temperatures, right? So let's say the beaker was, sitting in room temperature, which is, probably a little bit above 20 degrees Celsius. Let's just say it's 20 degrees Celsius in the room. Okay, if that's the case, then at 20 degrees Celsius, you can dissolve maybe about 30, it's probably a little bit over halfway, so maybe we'll say about 30 grams of KNO3 in 100 grams of water at 20 degrees Celsius. But if you warmed it up to 60 degrees Celsius, right, to here, the maximum amount of KNO3 you could dissolve is maybe like 110 grams of KNO3 in 100 grams of water at that temperature. So this happens, for most solids, as temperature increases, the solubility increases. Gases follow the opposite trend. As temperature increases, gases' solubility decreases. So that's just something to be aware of. Now, This curve, right, if you are on the line represents the saturation point, which is the maximum amount of solute you can dissolve in that amount of solution at that temperature. Okay? If you are underneath the solubility line, then you're unsaturated. If you're on the line, you're saturated. If you're above the line, it's what's called supersaturated. Okay, so like, let's say the beaker was at 40 degrees and I add, 25 grams, it would dissolve. I add 40 grams, it would dissolve. I add 50 grams, it would dissolve. Unsaturated, unsaturated, unsaturated. And then at some point here, it dissolves and we get saturation. If I added any more, it would not dissolve. Okay, so it's saturated only when you can't dissolve anymore. So in summary, if we had the curve, all right, when you're on the line, that's the saturated solution. Okay, if you're below the line, it's unsaturated. If you're above the line, it's supersaturated. Now you might be wondering, how can something be supersaturated? I thought saturated is when you have dissolved as much as you can at that temperature. And that's true. To get a supersaturated solution, what you have to do is you actually have to have a saturated solution at one temperature. Like let's say we have a saturated solution here at 60 degrees, and then we let it cool down to 40 degrees. The amount of solute that can dissolve at 40 degrees is less than at 60 degrees. Now, it was saturated here at 60 degrees, and it cooled down to 40. If it's cooling down, you actually will have a situation where there is going to be more solute dissolved in solution than should be possible at that temperature. You have created what's called a supersaturated solution. Now, this is kind of an unstable setup, and as soon as it's given the opportunity to, you will have some of the solute crystallize back out of solution. So you really just need to provide what's called like a seeding point or a crystal point. So if you had a supersaturated solution, and then let's say you just like dropped a crystal of KNO3 into the liquid, as soon as the crystal hit the liquid, crystals would grow off of it, and they would actually spread through the liquid and precipitate back out of solution or crystallize back out of solution. And the amount that would come back out is the difference between where it was saturated at 60 and where it's saturated at 40. The difference between that is what would precipitate or crystallize back out of solution. Okay? So these are some different parts and some different terms related to a solubility curve. But what we're going to do now is some practice problems. And the practice problems are not just going to have one curve on it. It's going to be a graph which has a bunch of curves, right? Most commonly, you have many substances plotted on the same graph, okay? Now, we have a whole bunch of things here, but you can see it says temperature on one axis and grams of solute per 100 grams of water. And as I mentioned, the general trend, it's not perfect, but general trend is that the solid substances, right, as temperature increases, the solubility tends to increase. And for gases, as temperature increases, the solubility tends to decrease. So a couple of general questions and then questions about interpreting it, like actually doing some kind of like calculations with it we will do. So general questions, points that collectively make up the solubility curve, meaning points on the curve for a substance represent A. All right, and so this is really just going back to this thing. The points that are actually on the line, those represent a saturated solution. Okay, so this is a saturated solution. The points that are below the curve for a substance, right? So again, going back to this, if we are below the line, that means we could still dissolve more. That's what's called unsaturated. In an unsaturated solution, you could add more solute and it would dissolve, and you could add more and it would dissolve. It's unsaturated all the way until you reach the saturation point. All right? The next question says, so let's turn this up. It says, the general trend for solids shows that right? For solids, the solid lines in general, as temperature increases, solubility increases. Right? So as temperature increases, solubility of solids generally increases. For gases, we have the opposite trend. Right? For gases, in general, as temperature increases, the solubility of gases, those are the dotted lines, decrease. Okay, so now we're going to interpret the solubility curves. We're actually going to do some finding some numbers and maybe doing some calculations. So number 1 says, how many grams of HCl would dissolve in 100 grams of water at 20 degrees Celsius? So this graph is showing you how much of a substance will dissolve in 100 grams of water. So they're asking about HCl at 20 degrees. So if we look on here and we find HCl at 20 degrees. So this is the line for HCl. Here's 20 degrees. So if I go up, 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 up until I hit this point right there. Okay. How much HCl can dissolve at 20 degrees in 100 grams of water? Well, this is 70. It's a little bit over 70. Maybe we'll say 71. Okay, so about 71 grams. Right, so maybe about 71 grams. Number 2, how many grams of HCl will dissolve in 100 grams of water at 60 degrees Celsius? So it's the same substance, but this time it's at 60 degrees Celsius. So we're going to go 60 degrees Celsius, up, 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 until we hit the line for HCl, which is right here. That's about halfway between these two lines. So if we go over, it's about halfway between 50 and 60. So about 55 grams. About 55 grams. So 55 grams. So those first two, all we're doing is, finding the temperature and then seeing where we hit the line for HCl. For number 3, it says, how many grams of KNO3 will dissolve in 100 grams of water at 15 degrees Celsius? So we're going to find the line for KNO3, right, which is a very steep line here. Here's the line for KNO3. At 15 degrees, so here's 10, here's 20, so 15, we're going to go up, 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 and we hit about right here. So how many grams is that? We're going to go over, and I'm just estimating here. It's, it's about halfway between 20 and 30. So maybe about 25 grams can be dissolved in 100 grams of water at that temperature. So for KNO3 at 25 degrees Celsius, we can dissolve about, at 15, this is 15 degrees Celsius, we can dissolve about 25 grams. All right. So that's approximately our answer for number 3. Number 4 says, which substance is the least soluble? Now, least soluble means that you cannot dissolve very much of it, and they're asking about 10 degrees Celsius. So if we're looking on this chart, okay, at 10 degrees Celsius, something would be really soluble, like if you look at Ki up here, look at 10 degrees, you can dissolve like 135 grams of it. That's a huge amount to be able to dissolve. That's very soluble at 10 degrees. But they're asking what's the least soluble at 10 degrees. So the least soluble is the one that's going to be lowest down. It's going to be this one, right? The lowest line at 10 degrees. And that is the line for KClO3. It's going to be the least soluble at 10 degrees Celsius. So KClO3. Number 5 says, at what temperature do NH4Cl and Na2SO4 have the same solubility in water? So to have the same solubility, that means that the two lines are going to intersect. They're going to cross. So maybe one is going like this and the other is going like this. Where they cross, that point would mean that at that temperature they can dissolve the same number of grams. They have the same solubility at that temperature. So we just need to see where those two lines cross. So NH4Cl and Na2SO4. Okay, so let's find them on here. Here's NH4Cl, this line, NH4Cl, and the other one's Na2SO4, which is here. So we have to see where those lines cross, which is right here, it looks like, right? That's where, here's NH4Cl, here's Na2SO4, they cross. So the question asks, at what temperature do they have the same solubility? So we're finding, actually, on this case, we're finding the temperature. So we're going to go down here. And I'd say it's a little bit less than halfway between. So if you said like 43 degrees Celsius, I'd say that's, that's about, about 43 degrees Celsius. We're estimating, but that's a pretty good answer. Now, number 6 is kind of like we did in the first 3, but it's a little different. It says, how many grams of KClO3 are required to saturate 200 grams of water at 10 degrees Celsius? So if we look on this chart, they're asking about KCl at 10 degrees Celsius. So if we look at this chart, KCl is this line at 10 degrees. So we're right here, okay, which is 30 grams. So 30 grams can dissolve in 100 grams of water at 10 degrees, okay? So I'm going to jot that down here. And what we're writing is 30 grams can dissolve in 100 grams of water at that temperature. This question's asking you, how many grams could dissolve in 200 grams of water at that same temperature, right? Because if you could dissolve 30 grams in 100 grams of water at that temperature, if you have twice as much water, how much could you dissolve? Okay, now you could just do the math here. It's like a equality thing, solve. But on a logical level, if you can dissolve 30 in 100, if you had twice as much water at the same temperature, you would dissolve twice as many grams. So this is going to be about 60 grams of KClO3 could dissolve in 200 grams of water at that temperature. So really, even though our graph shows how many could dissolve in 100 grams, we just find that number and multiply it by 2 because we have twice as much water. 7 says, a saturated solution of NaNO3 is formed from 100 grams of water. If the saturated solution is cooled from 70 to 25, how many grams of precipitate will form? So we just need to find how much NaNO3 can dissolve at 70 degrees and how much can dissolve at 25 degrees. And the difference between those two is what's going to precipitate out when it cools. Okay? So we just have to find those 2 points. NaNO3 is what we're interested in. The temperatures are 70 and 25. So let's see if I can fit this on the graph here. 70 degrees, we're going to go up, 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 up until we hit the line for NaNO3, which is right here. Let's say that's pretty close to 135, right? Pretty close to 135. It's between 130 and 140. And then it's going down to 25, which here's 30 and here's 20. So 25 is halfway between these lines, which is right here, which is about 90. So at 70 degrees, we can dissolve 135. At 25 degrees, we can dissolve 90. They asked if we had a saturated solution here and it cooled down to here, how much of it would precipitate back out? And the answer is just the difference between these two, right? If we have 135 grams dissolved and it cools down so that only 90 of it can dissolve, right? Only 90 of the 135 can be in solution. So the other 45 is going to crystallize back out, precipitate back out. So in terms of our numbers here on the page, it's just 135 grams minus 90 grams gives us 45 grams is what will not be able to stay dissolved in solution. So number 8, this is about as complicated as they get. It says 400 grams of water is used to make a saturated solution of KNO3 at 45 degrees. How many more grams of KNO3 could be dissolved if the temperature were raised to 70 degrees? So yes, it's 400 grams. But first we just need to find how much KNO3 can be dissolved at 45 degrees on our chart. Okay, so on our chart, KNO3 at 45 degrees. So 45 is about halfway between these two lines. It's probably about right here, which is about 75. About 75 grams. And it's asking how many more grams could be dissolved if the temperature were raised to 70. And 70 is actually a little bit off the out of our zoom right here, but 70 degrees. I'm going to go up until I hit the line for KNO3, which is actually up here. Okay, and I'm maybe estimating a little bit. It's about 140. Okay, so at 45 degrees we have 75, and at 70 degrees we have 140. So if we can dissolve 75 at this temperature, and we can dissolve 140 at this temperature, that means that we can dissolve 65 more grams at that higher temperature, right? So in terms of what we have to do with this problem, if at 45 we can dissolve 75 grams, and at 70 we can dissolve 140 grams, then 140 grams minus 75 grams equals 65 grams, right? So if this was at 100 grams and we made a saturated solution at 45, we would have to add 65 more grams to make a saturated solution at 170. But it's not 100 grams of water, it's 400 grams of water. So it's not going to be 65, it's going to be 4 times that amount, because 65 is what's needed in 100, right? So writing it like an equality, 65 grams is needed for 100 grams. They're wondering how many grams is needed for 400, right? So really 65 times 4 gives us 260, right? So 65 times 4, that is our answer. So this is all just a variety of problems related to solubility curves. The most important thing is you understand when you're reading a solubility curve, the curve most typically is showing you how much of a solute can be dissolved in 100 grams of water at a certain temperature. Okay, so you find that amount in 100 grams. And if you have more than 100 grams, then you would multiply that amount by, let's say, 2 if it was 200 grams, or times 3 if it was 300 grams, or if it was 350 grams of water, then maybe you'd have to multiply by 3.5, okay? Hopefully you get the idea there. This has been a video all about solubility and solubility curves from our unit on solutions. Hopefully you found it helpful. Keep working, keep up the good work, study, study, study. See you back in class.